So today we're going to talk about thermochemistry and in particular Hess's Law. So we've talked about enthalpy in terms of internal energy where, and this is such an important picture, I don't care if you've just watched the video, I'm going to explain it again because this is a key idea. If you have some sort of heat source into a container, if the heat that goes in, Q, goes into the molecules, that defines the internal energy. So you can say that the heat capacity is du dt at constant V. Whereas if the heat that goes in under constant pressure conditions, that goes into the molecules, so internal to the molecules, but it also goes into expanding the container to maintain constant pressure. So you've probably heard that the enthalpy is defined at constant pressure, but you can have an enthalpy with pressure changing all the time, but it's defined at constant pressure, and it's a very, very subtle distinction. Okay, so enthalpy is equal to U plus PV, and so the delta enthalpy is equal to delta U plus delta PV. And typically pressure is held constant under enthalpy conditions, and so that's one of the reasons that you'll a lot of times see this. Okay, so I want to zoom in on the heat capacity under constant, the heat capacity specifically representing the enthalpy when you have a change in pressure. Cool? Okay. Oh, no, I lied. Nope. Sorry, we are just going to just focus in on here. Never mind. No change in pressure, just change in temperature. Cool. Okay. Pause so I can erase. All right. So we have our system and heat goes in. And so now we're under constant pressure. So constant pressure. So we have Q sub P, an inexact differential from T1 to T2. So we're heating it from T1 to T2. And so that's going to equal the infinitesimal change of the heat, which is path dependent. So the Q depends on the path, whereas what we're about to relate it to, which is enthalpy, depends on the state. Two different things. All right. So one cool thing that we can do here is we're going to say that I want to know what is the change in my heat per change in temperature, but I'm going to integrate over temperature. Cool, so I basically just multiplied by 1 here, dt over dt. You can't tell it's a dt. So dt over dt, multiply it by 1, but then what's really neat, the change in heat at constant pressure per change in temperature, that should look familiar. That is just partial H partial T under constant pressure, which is also equal to the heat capacity at constant pressure. And so if we want to look at what happens when you are heating something, what's the heat associated with a constant pressure condition, you can integrate the heat capacity with respect to temperature across the temperature range that you change the system under, and that should give you your heat. And so what's great about this is if Cp, so Qp is equal to Cp dt from T1 to T2, if Cp is independent of temperature, which for most of the systems that we'll be looking at, it is, but you can take that out of the integrand, which then leaves Cp integral T1 to T2 dt, which is just your very favorite C delta T. So Q under constant pressure conditions is equal to C delta T, and this would be your enthalpy. Or actually, I should say it's change in enthalpy. And so when you've been dealing with heat up to now, like in Chem 116, you saw MC delta T. Ta-da, there it is. Okay, so there is that. Oh, another thing I should mention is if Cp does depend on temperature, what you would then have to do is take into account, so from this step, before you can go on to this step, you couldn't go on to this step, you would say, all right, well, what is the T2? So Cp is a function of T dt, what is the function? And this is where chemical character comes in. So there isn't an elegant way to say, oh, well, this is how the heat capacity always depends on temperature. It depends on the system. If you're dealing with liquids, if you're dealing with solids, if you're dealing with alloys, if you're dealing with what kind of alloy, with what kind of solid, with what kind of liquid, with what kind of mixture, is there salt present, is there not salt present, do you have high solute, low solute? Theory after theory. This is where material science comes in, is trying to understand what's the fundamentals behind the different materials, and if we can find one of those for all systems, that would be the theory of everything. Well, not just for heat capacity, that would be describing any system with just one or two equations. Okay, so it's common that a polynomial fits with a series of arbitrary fitting parameters, and I shouldn't call them arbitrary. They're not arbitrary, they just don't necessarily have physical meaning. And so the common one is, where's my notes? So CP is typically represented by a polynomial CP, and actually this will be molar heat capacity. Forgive me, these should all be molars. Anywhere you see a heat capacity, it's going to be molar heat capacity. It's never going to be just heat, like specific heat. Okay, so that's joules per mole per Kelvin. Okay, so that would normally be some sort of coefficient plus another coefficient times temperature plus another coefficient divided by T squared. This is typically what the heat capacity follows most of the time. And so what you would do is you would take this function, stick it in here, and then you would integrate a dt plus integral bt dt plus integral c over t squared dt over the different ranges. And then that would then give you what your heat is. Most of the time we assume that the heat capacity is independent of temperature, and so then you can make that step. Back to my statement about you can't just memorize these equations. You have to make that assumption, and you'll, in your homework, you'll say, I'm assuming heat capacity is independent of temperature, and then you allow yourself to make that next step. Now you start to see when we tell you in, say, the labs that you perform, like what kind of sources of error might you have, and you're like, a gust of wind came through and it messed up the balance. That's crap, that didn't happen. An actual possible uncertainty would be, well, I've made an assumption that my heat capacity is independent of temperature. If I'm pretty close to a literature standard value, that's great, you could make that assumption. But what if you don't have a standard value? So if you make that assumption, you can say, well, there could be some uncertainty in determining my heat because I have assumed that my heat capacity is independent of temperature. If it were to be dependent on temperature, you'd have to go into the lab, you'd have to do this experiment, determine what the heat capacity is as a function of all these temperatures, get the empirical relationship, put it back in to determine what your Q actually would be. Go team. So that would be a place where you would talk about when you would make that assumption. For your homework, you just be like, I'm going to make this assumption. Or it might be wise to not make that assumption, as the homework problem would say, you cannot assume that heat capacity is independent of temperature. Okay, I'm going to pause and erase this. Okay, one really cool thing I want to show you about heat capacity, I just absolutely love this. So H is equal to U plus PV. And so if I say then that if I have an ideal gas, I can say the enthalpy is equal to internal energy plus nRT. And then what I can do is, well, make this molar, so divide out by N. So molar enthalpy is equal to molar internal energy plus RT. Now I can say, all right, I'm going to take ddt of the whole thing. And so this becomes dH dt is equal to du dt plus dRt dt. Cool. And so this essentially then becomes, essentially there's a couple other steps, but as in, well, you'll see. So this is the heat capacity at constant pressure, heat capacity at constant volume, plus R. Brilliantly awesome. For an ideal gas, the difference between the heat capacity at constant pressure and the constant volume is going to be your gas constant. Cp minus Cv equals R. Explain that to me. Seriously, you should. You should be able to. This is a beautiful relationship between the two heat capacities, and I think it really shows you the difference between these two pictures. Okay, so here's my candle, the infamous PChem candle. All right, so this is my constant volume system, and this is my constant pressure system. So Cp, Cv. This is equal to partial H, partial T, constant pressure. This is equal to partial U, partial T, constant volume. Heat energy goes into the system. It goes into the molecules. Constant volume conditions. Internal to the molecules, it goes into delta or du. Heat capacity at constant pressure. To maintain constant pressure here, heat goes in, but it has to maintain constant pressure, which means there's an expansion. And that expansion is going to be in addition to the heat going into the molecules. So you've got enthalpy is equal to U plus PV. So internal to the molecules plus the additional PV work associated with expanding the box. The difference between those two, and this is the difference between Cp and Cv, the heat that goes in at constant temp, or the heat that goes in to raise the temperature minus the heat that goes in to raise the temperature, the difference between those is R. I can't emphasize enough the importance of this constant. We'll get to what it is in just a little bit. But I really want you to think and stew on what is R. You could say 8.314 joules per mole Kelvin. And we'll spend a lot more time thinking about what this means. But joules per mole Kelvin, stew on that. Okay, one more thing, then I'm done with this video. Okay, Hess's Law. Hess's Law is kind of the fundamental of thermochemistry that you've seen. I mean, we introduced that in Chem 115. And you probably saw it a little bit in high school. But there is so much, there's a lot of misunderstanding when it comes to Hess's Law. So we're going to really dive in deep on this one. So it's the standard reaction enthalpy. So the standard reaction enthalpy is the sum of values for individual reactions into which the overall one may be divided. And you might remember this, that you can add up the different enthalpies of reaction and then subtract off some of them. So you get the overall one. And it looks something like this. Delta H of a reaction is equal to the sum of delta H of formations of your products. And actually I'm going to put the stoichiometric coefficient, that's the number of moles, minus the delta H, number of moles of formation of your reactants. Products minus reactants. Let's keep going. What this means, enthalpy. So we've got, here's our reactants, here's our products. Okay, and this is an energy diagram. And so you may have seen this in terms of, well, a picture that looks something like this, to where you've got reactants and products. We're not going to represent that yet because that's going to have different meaning when we get to kinetics. But here we've got reactants to products. This is our delta H of reaction. Okay, this is breaking everything up into its elements. So if you have O2 plus H2 yields 2H2O, here would be O2 and H2, and actually there should be two of those. And then here you would have 2H2O. But up in the elements part, you have an oxygen, a hydrogen, 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 and hydrogen. You've broken up everything. Now, does it take energy or does it give off energy if we break it up into its elements? If you said I got to get this right. If you say that when it breaks up into its elements, it gives off energy, that's for you. I'm going to slap you. Slap yourself. You need to slap yourself. It takes energy to break bonds. It takes energy to break them. This motion is bad when you think that the bonds are breaking. It takes energy, something that I can rip. It takes energy to break them apart. You have to put energy into it. Okay? So because this takes energy, it goes up to its elemental form. So there's a delta H associated with this part. Then when it goes from broken up to forming new bonds, this is what the second law of thermodynamics loves it, the system will go to the lowest energy state. When it does that, it's going to choose between going back to O2 and H2 or going to 2H2O. It's always going to choose the lower energy state, it being the reaction. And so that means that this delta H, because energy is given off when bonds form, there's your delta H of the formation. Now, let's go back and read Hess's law. Or I should say, you probably know, so this would be, so this delta H1 minus delta H2 gives you delta H of the reaction. Well, delta H1 minus delta H2 gives you the overall reaction, delta H of reaction. The standard reaction enthalpy is the sum of values for individual reactions. Those individual ones can be theoretical. They can be fake as long as they yield the final product, which it does. It doesn't actually happen this way. You don't have little hydrogens and oxygens like all breaking apart and then all finding their friend and then all getting back together. No, that's not the way that mechanisms happen. But that's how we theoretically depict them, which means that Hess's law works and we just add these things together. And as long as our sign convention is correct, we're good in terms of determining the enthalpy. Okay, cool. So we've got, yes, biggest thing, takes energy to break a bond. So every time you felt an exothermic reaction, it is not bonds breaking. It is not, under no circumstances. Fuck the people that say that it is because bonds are breaking. Grr, it's not true. Sorry, I didn't mean to offend anybody. Actually, yeah, people do say that. It's the biggest misconception that when bonds break, they give off energy. That is bullshit. When bonds form, they give off energy. Because when you go from an unstable condition to a much more stable one, you have given off that excess energy. That's Hess's law. It takes energy to break a bond. And when bonds are formed, they release energy. You can tell I'm very serious about this one. Okay, last off, Kirchhoff's law. I'm going to pause, erase, and be back. Never mind, I think I will do a podcast on Kirchhoff's law. Go team.